Hello friends, today we will explore new frontiers in the search for dark matter. In this video, we will dive into how studying exoplanets orbiting other stars might provide cosmic clues needed to solve one of the biggest mysteries in the universe. Discover how these distant worlds could act as natural detectors for dark matter and what scientists are looking for in their data, and how this is going to give yet another means for studying the dark matter. Let's go. Welcome, all cosmic explorers. Have you ever looked up at the night sky and felt a profound sense of wonder that the vast, sparkling canvas holds countless secrets, and perhaps the biggest one of all is the dark matter? It is invisible force that shapes galaxy, but we can't see it, we can't touch it, or we can't even directly detect it. Yet it is everywhere. For decades, scientists have been on relentless hunt for this elusive substance, using everything from massive underground detectors to particle accelerator. But what if the answer isn't deep beneath our feet or in the powerful collisions, but rather light years away? What if the very same distant worlds we are discovering every day, which are also known as exoplanets, hold the cosmic clues we need to finally, which will help us crack the dark matter code? Today, we are going to dive into this fascinating new frontier in the search for the universe's missing mass. First, let's establish what we are talking about. What exactly is dark matter? Imagine you're watching a program, or some sort of a watching through the telescope, and if you know the weight of the people on it and how fast it is spinning, you can calculate the force needed to hold everyone on. Now imagine a galaxy like our Milky Way spinning majestically. When astronomers calculate the mass of all the stars, gas and dust that we can see, it's simply not enough to hold the galaxy together. The outer stars should be flung off into space, yet they are not. This discrepancy led to the hypothesis of dark matter, an invisible, mysterious substance that provides the extra gravitational glue. It doesn't emit, absorb, or reflect light, which is why it is dark. It is estimated to make up about 27% of the universe's total mass and energy content, while the ordinary matter that we are made of only accounts for tiny 5%. The rest is dark energy, but that is a story for another time. We are not talking about dark energy today. Its existence isn't just a theory. We have compelling evidence from the galactical rotations, the formation of large-scale structures in the universe, and the phenomena like gravitational lensing, where the immense gravity of the dark matter warps light from distant objects. It's invisible scaffolding upon which the universe is built. Without it, the galaxies wouldn't form as they do, and we wouldn't be here also. So finding it is just a scientific curiosity. It's a fundamental to understanding our cosmic origins. For decades, scientists have tried to directly detect dark matter particles. The leading candidates are the WIMPs, which stands for weakly interacting massive particles. The idea is that these particles occasionally, very rarely, might interact with ordinary matter. So we have built incredible sensitive detectors deep underground, shielded from the cosmic rays, hoping to catch a stray WIMP hitting an atomic nucleus and causing a tiny measurable recoil. Think of it like trying to catch a ghost in a dark room using a microscopic bell that rings only when the ghost might bump into it. We have smashed particles together in accelerators like Large Hadron Collider, hoping to get a WIMP in powerful collisions, mimicking the conditions of the early universe, but so far, no luck. These experiments have set tighter and tighter limits on what dark matter could be, but the particles themselves remain elusive. The problem that dark matter interacts so weakly that it might pass right through us and even entire planet without a trace. It's like trying to catch a specific fish in an ocean where the fish is transparent and almost never touches anything else. This is where the exoplanet comes into the picture, offering a radically different approach. Instead of building a bigger, more sensitive detector on Earth, what if we use entire planets as natural detectors? Exoplanets are incredibly diverse, from scorching hot lava world to frigid ice giants and even potentially habitable planets. And they exist in vast numbers. The universe is teeming with them. The basic idea is that if the dark matter particles, particularly some types that haven't been ruled out yet, interact with ordinary matter, they should be passing through exoplanet all the time. But unlike our terrestrial detectors, which are tiny by comparison, an entire planet is massive target. And here is the kicker: if the dark matter particles accumulate in a planet's core or interact with its interior, they could leave a detectable signature. Think of it this way: Earth-based detectors are like trying to catch a few raindrops in a big rainstorm. Exoplanets, especially large or dense ones, are like trying to catch those raindrops in an entire ocean. The sheer volume and density could significantly increase the chance of interaction and accumulation, potentially leading to observable effects. So, what kind of signatures we are talking about? One intriguing idea involves heat. If certain type of dark matter particle accumulate in the core of an exoplanet, they could annihilate each other or simply scatter off ordinary matter, generating heat. For planets that are too cold or too far from their stars to be naturally warm, this extra heat from dark matter could be a telltale sign. Scientists are particularly interested in brown dwarfs and old isolated gas giants. Brown dwarfs are often called failed stars because they are too massive to be planets, but not massive enough to ignite hydrogen fusion like a true star. They slowly cool over billions of years. If we observe a very old brown dwarf that is hotter than it should be, the anomalous heat could be the strong indicator of the dark matter interacting with its core. This dark matter heating would manifest as a subtle but persistent internal warmth. Another possibility is that the dark matter could affect the composition of the dynamics of the exoplanet's atmosphere. While this is a more speculative area, some theory suggests that the interaction could be subtly alter atmospheric chemistry or even contribute to atmospheric escape over vast time scales. So, by studying the atmospheres of many different exoplanets, we might find statistical anomalies that point to the dark matter. This is particularly exciting as our ability to characterize exoplanets' atmosphere is rapidly advancing with telescopes like James Webb Space Telescope. How do we actually look for these subtle signs from light years away? We use powerful telescopes both on Earth and in the space. Mission like Transiting Exoplanet Survey Satellite, that stands for TESS, have discovered thousands of exoplanets, giving us a vast catalog to study. The Hubble Space Telescope has provided invaluable insights, and now the James Webb Space Telescope JWST is revolutionizing our ability to peek into exoplanets' atmospheres. JWST, with its incredible infrared capabilities, can analyze light that passes through an exoplanet's atmosphere. When it transits in front of its star, this allows us to detect specific molecules and gauge atmospheric temperatures. If we can precisely measure the temperature of an old isolated exoplanet, or brown dwarf and find it's warmer than it should be based on age and stellar radiation, that could be our cosmic clue. Future missions like European Space Agency, Plato, and Ariel telescopes will further enhance our ability to characterize exoplanets, finding even more worlds and studying their properties in unprecedented details. This continuous flow of data will provide a treasure trove for researchers looking for those elusive dark matter signatures. The sheer number of exoplanets are now, we are able to study, and the depth of the information we can gather about them makes this a truly golden age of this kind of interdisciplinary research. This approach is so exciting because it brings together two seemingly disparate fields: exoplanet science and particle physics. It highlights the interconnectedness of a universe where discoveries in one area can profoundly impact another. It is a testament to human ingenuity that we are willing to look for answers in the most unexpected places. Even if the exoplanet don't lead us directly to dark matter, this research pushes the boundaries of our understanding of both planets and fundamental physics. It helps us refine our model of planetary interiors, atmospheric evolution, and the very nature of the matter itself. Every null result, every ruled out possibilities bring us closer to the truth. From the smallest subatomic particle to the largest galactical structure, the universe is a puzzle, and dark matter is arguably its biggest missing piece. Whether the answer lies in our terrestrial labs or on a distant alien world, the quest continues. And with every new exoplanet we discover, every new piece of data we collect, we are not just finding new worlds, we are gathering more cosmic clues in humanity's grandest detective story. So friends, what do you think? Do exoplanets hold the key to unlocking the dark matter mystery? Let us know your thoughts in the comment section below. If you enjoyed this journey into the cosmic unknown, please like this video, subscribe to our channel for more scientific exploration, and hit that notification bell so you don't miss out any new next adventure. So thank you for joining me on this cosmic clue episode. Until next time, keep looking up and keep wondering. The universe has so much to tell us. Bye for now. See you in the next one.